Okay, 7.2 photoelectric effect. Okay, so what is photoelectric effect? Okay, when a metal surface is illuminated by a beam of light at a certain frequency, electron can be emitted from the metal. This phenomenon is known as photoelectric effect. So basically, got light shine on the metal surface, and the energy from the light is absorbed by the electron on the metal surface. So when the energy absorbed from light is enough, then the electron will be able to escape from the metal surface. So why is it that we only talk about metal? Because metal is the one that easy to have photoelectric effect. Okay, metal is the one that easy to have photoelectric effect because metal have more free electron. Okay, metal have more free electrons, so these free electron, when they absorb enough energy, then it will be able to escape. Okay, escape, and so the electron that escape, we call it photoelectron. Okay, photoelectron. Photoelectron. Okay, so photoelectric effect. Okay, now the characteristic of photoelectric effect can be studied by arranging a photocell in the circuit as shown in figure 7.7. Okay, here we have a photocell, and on the surface of this photocell we have a light sensitive metal. This light sensitive metal is basically just a metal that need less amount of energy for electron to escape. There are a lot of different metallic elements. Okay, there are a lot of different metal, right? We have iron, gold, copper, silver, aluminum, magnesium, and so on. Okay, there are a lot of different metal, but and different metal, they need different amount of energy for the electron to escape. Some metal only need a little bit of energy for the electron to escape. Some metal need more energy. So when we say that we have light sensitive metal, basically the metal that we put here is a metal that need low amount of energy in order for the electron to escape. Okay, so you see between the light sensitive metal and the anode here, there is a vacuum. Okay, vacuum. So that means there's nothing here, no air. Okay, so this anode is connected to the positive terminal of the battery, and the light sensitive metal is the cathode because it's connected to the negative terminal of the battery. So when there's no light, okay, when there's no light, no photoelectric effect. So that means no electron can pass from the light sensitive metal to the anode, from cathode to anode, no electron. So if no electron, that means no electric current. Okay, so what happens is when you shine a light onto the light sensitive metal, then photoelectric effect will occur, and the milliammeter will show a reading. So the reading of the milliammeter will means that there is electron, there is current that flow. Okay, current can flow in this circuit. So so the only reason that current can flow is electron can pass through this gap. Okay, electron can pass through this gap. And how is it that electron can pass through this gap? Due to photoelectric effect. That means when there's light, there's current. When there's no light, there's no current. Okay? Alright, so let's look at here. When a light sensitive metal surface cathode is illuminated with a certain light beam, electron will be emitted from the metal surface. These electrons are called photoelectron. Okay? The emitted photoelectrons are attracted to the anode, which has positive potential. The movement of the photoelectron from the cathode to the anode produce a current inside the circuit. The milliammeter show the value of the current. Alright. Okay, look at this activity 7.5. To determine the value of Planck constant using the Planck constant kit. Okay, so this Planck constant kit consists of a 9 volt battery, 1 kilo ohm potentiometer. Okay, so this is the potentiometer. LED of different color, milliammeter and voltmeter. Okay, so this potentiometer basically is like a variable resistance. Okay, this potentiometer, it has different function. That means it can function as a resistance, it can function as a rheostat, and it can also function as a potential divider. Okay, so this is a potentiometer. How does it work? Actually, is not so important here lah. Okay, so the important thing here is that we find out that. Okay, let's go through the instruction. Okay, using the red LED, connect the Planck constant kit as shown in figure 7.8. Scan the QR code to print the table. Okay, the table is this table lah, table 7.2. Alright. Adjust the knob on the potentiometer to obtain the voltage. V equals 0.2 volt. That means this voltage. Okay, that means the voltage between the LED and between the LED is 0.2 volt. You see this voltmeter is connected between the LED. So this 0.2 volt is the voltage that is obtained by the red LED. Okay. Record the milliammeter reading. Repeat step 3 for 0.4, 0.6, 0.8 and until 3 volt. Okay. Draw a graph of current against voltage. Based on the graph, intercept value on the voltage axis. Determine the activation voltage of the red LED. Okay, so the activation voltage, meaning the voltage where the red LED can light up. Okay, and then we repeat using orange, green, and blue LED. Okay, so what is it that we can find out is that the different color. Okay, so what is it that we can find out is from the graph. So after we do the experiment, let's say with red LED, okay, let's say this is red LED. Okay, so what is it that we find out is when the voltage is low, the red LED will not be able to light up. So you need to increase the voltage of the red LED until reach a certain voltage. Then after that, the red LED will be able to let current to pass through. Okay, then only current can pass through the red LED. So you see, before a certain voltage, there is no current at all. Okay, the current is 0. That means no current can pass through. And when reach a certain voltage, then suddenly got current can pass through. Okay, got current can pass through, and as the voltage increase, the value of the current increase. Okay, so maybe you would think, what is so special with this? Isn't this the same with a normal bulb? Actually, it's different from normal bulb. If a bulb, the graph is not going to be like this. Okay, if it's a graph, if it's a incandescent bulb, the normal bulb, okay, the filament bulb, the graph is not going to be like this. The graph will be look like directly proportional. Okay, that means this don't care what voltage is it, current will be able to flow through the filament bulb. Whether the filament bulb can light up or not, that is another story. But current can still pass through the filament bulb even though the voltage is low. Okay, but for LED there is a certain activation voltage. Okay, so this VA, this is the activation voltage. Okay, activation voltage. And we can find out that when we change the red LED to LED of different color, okay, to orange LED, we find out that the activation voltage of orange LED is higher. Okay, the orange activation voltage of orange LED is higher than the red LED. And we find out that the the green, orange first, and then the green is higher, and last, blue is the highest. Okay, like that. So why like that? Okay, why like that? Why is it that different color LED have different activation voltage? Okay, the reason is the electron. The reason is different color of light have different wavelength. Okay, have different wavelength, and if they have different wavelength, it means the frequency of the light will be different, right? So for example, this wavelength, okay, this is a big wavelength. So if the wavelength is big, that means the frequency of red color, okay, the frequency will be low. Okay, longer wavelength means lower frequency. And this one, from red to orange to green to blue, you see the wavelength becomes shorter. And when the wavelength becomes shorter, it means that the frequency of the color will be, the frequency of the wave will be greater. So from what we learned previously, energy of the photon equals to Planck constant times the frequency of the photon. It means that in order for red color photon to come out, you need less amount of energy, because frequency low, that means the energy required will be lower. Okay, that means the energy of the red color photon is lower. So you don't need to have high activation voltage, because if the activation voltage higher, that means more energy is supplied to the LED. Okay, get the idea? So if frequency is low, energy for the photon is low, so that means you don't need to have a high activation voltage. So the activation voltage will be low. Okay, and from when go towards blue, frequency high, so that means the energy for the photon will be higher. So if the energy of photon is higher, that means you need to supply more energy to the LED. So the activation voltage for blue LED will be higher. Okay, so look at here, this is the inverse of wavelength. So this one is big, so inverse, so that means you get a small number. Okay, small number here. Here you will get a larger number. Okay, you get a larger number. So that means this inverse of the inverse of the wavelength is small, then the activation voltage is small. Inverse of the wavelength large, then the activation voltage is large. So we take this and we plot a graph. We plot a graph using the activation voltage and the inverse of wavelength, and we can get this graph. Okay, we plot a graph of activation voltage against 1 over wavelength. So what is it that we can find out is that the higher the inverse of wavelength, okay, the higher the activation voltage. Basically, it just means that the shorter the wavelength, the higher the activation voltage. Okay, so from here we can calculate the Planck constant. Okay, from this graph we can calculate the Planck constant. Okay, so from this graph we can calculate the Planck constant. So you see that here is already given that the gradient is equals to Planck constant times the speed of light over E. What is E? E is the charge of one electron. Okay, charge of one electron. So how is it that we get this Planck constant times the speed of light over the charge of one electron? Okay, so first the gradient of the graph. Okay, gradient of the graph. So this gradient will be the activation voltage over the 1 over lambda. Okay, right. So changes in the activation voltage over changes in the inverse of wavelength. Okay, so that means we can get that the gradient will be the activation voltage times the wavelength. Okay, and from wavelength, from the activation voltage. Okay, what is voltage? Voltage is work done per unit charge. Okay, work done per unit charge to go from one point to another point, right? Okay, the definition for potential difference. Okay, so this work done means that energy. Okay, this work done means energy, and the charge. The amount of charge that we are talking about here is amount of charge of one electron. So we represent it with a small e. Okay, small e to represent the charge of one electron. So basically, the activation voltage will be the amount of energy needed to have needed to make one electron escape. That means have photoelectric effect. Okay, so this will become energy over the charge of one electron. So this is the energy of one photon. Okay, the energy of one photon, because the energy that is needed for one electron to undergo photoelectric effect is the energy from one photon. Okay, it's the energy from one photon only. Alright, so this one wavelength. And because this E is energy of one photon, okay, because it's energy of one photon, so that means we can substitute this with E equals to Planck constant times the frequency. Okay, so this is Hf over E. Alright, so this F lambda, okay, F lambda, Hf lambda over E. So from speed of light equal to the frequency of light times the wavelength of light. Okay, this is from the wave equation, V equal F lambda. So the wave speed substitute with speed of light. Okay, C equal F lambda. So that means this F lambda can be substituted with speed of light, C. Okay, so over E. So that is how we get the gradient of the graph equals to the Planck constant times the speed of light over the charge of one electron. Okay, so in order to get the value of Planck constant, all we need to do is to take the gradient times the charge of one electron divided by the speed of light. Then we will be able to get Planck constant. Okay, so H is Planck constant. Okay, so now we want to look at the characteristic of the photoelectric effect. Okay, the higher the frequency of the photon of light, the higher the kinetic energy. Okay, this characteristic of photoelectric effect is very important. You must know all four of the characteristics. Okay, the first one, the higher the frequency of the photon of light, the higher the kinetic energy of the photoelectron emitted from the metal surface. Okay, so that means if you have that means if you shine a light onto the metal and the frequency of the light is higher, that means that the photon will have higher frequency, and the photon have higher frequency, that means the photon have more energy. So the electron that absorb photon of higher frequency, that means the electron will be able to get more energy. Okay, electron get more energy, so the kinetic energy of the photoelectron will be higher. Okay, so next, the minimum frequency of light needed for a metal to emit electron is known as the threshold frequency for that metal. Okay, so basically it means that if the frequency of light is not high enough, then it will not be able to produce a photoelectric effect. Okay, actually although we use the word light, but the light that we are talking about here is electromagnetic wave. That means it not necessarily visible light, understand? Not necessarily visible light. Actually, the light that can produce photoelectric effect is for a normal metal, okay, for a normal metal, even the lowest one will be outside of the range of visible light. That means it is within the range of ultraviolet ray. Okay, I repeat, even the lowest frequency of light that can produce photoelectric effect is actually ultraviolet ray. Okay, ultraviolet. That means if you shine with a normal light, with visible light, that means no photoelectric effect. Okay, no photoelectric effect. Okay. Next, the kinetic energy of photoelectron does not depend. Kinetic energy of photoelectron does not depend on the intensity of light. An increase in light intensity does not produce photoelectron with higher kinetic energy. So that means if the light is brighter, okay, it can produce more photoelectron, but the photoelectron that is produced will not have higher kinetic energy. Okay, the kinetic energy of the photoelectron depend on the frequency. That means if the frequency of light is higher, then only the kinetic energy of the photoelectron will be higher. Okay, and then the last one, photoelectrons are emitted instantaneously when a metal surface is illuminated by light. That means when a light shines on the metal surface, immediately electron, if the frequency is high enough, okay, when the light shine on the metal, immediately the electron can escape. Okay, if the frequency is high enough, when the light fall on the metal surface, immediately it can produce photoelectric effect. That means every electron only absorb energy from one photon. Okay, it will not be able to absorb energy from two photons. So that means the frequency of the photon must be high enough. Okay, it must be high enough so that when the electron absorbs the energy from that one photon, then it will immediately get enough energy to escape. And the higher the frequency of light, that means the higher the energy that is carried by the photon. So when the electron absorbs the energy from that one photon that have higher frequency and higher energy, then the electron will have more kinetic energy. Okay? Okay, so to stress, the threshold frequency, okay, is the minimum frequency required to produce photoelectric effect on a metal. Okay, so to summarize a bit, okay, to summarize a bit is actually like this. Okay, so this is metal surface. So the metal surface have electron. Okay, have electron. So when the electron get enough energy, it will be able to escape and become photoelectron. So let's say got light. Okay, the light shine. So when the light shine, the energy of light is transferred in the form of photon. Okay, in the form of photon. Okay, in the form of photon. So the energy of the photon will be higher if the frequency of light will be higher. That means for example, red light, the frequency is low. That means the energy of red light is low. Blue light have higher frequency, so the energy of photon of blue light will be higher. So if you want the energy to be even more higher, then the frequency will need to be even higher than blue light. So the higher frequency than blue color light, it will go into ultraviolet. Okay, it will go into ultraviolet, the range of ultraviolet. So that means the photon from ultraviolet ray, UV ray, it will have more energy, and the energy will be enough to cause the electron to have photoelectric effect. Okay, so that means every single photon of let's say this is UV. Okay, this is ultraviolet. Okay, ultraviolet. So this ultraviolet have enough energy, or the frequency is higher than the threshold frequency. Okay, if the frequency of the ultraviolet is higher than the threshold frequency, then the photon will have enough energy to produce photoelectric effect. Okay, so one electron, the probability, the chances of one electron to come into contact with one photon is actually not very high. Okay, it's actually very low. Because the reason is very simple. You imagine that the electron is very small, right now. All of the electrons are very small, and photon is even much more smaller than electron. So in order for the electron to meet with one photon, the probability is actually very low. So that means the probability for one electron to absorb energy from two photons, that means the chances for one electron to meet two electrons simultaneously, that means after one electron go in, after one photon go into the electron, another photon immediately also go into the electron, is very low. It's so low that we say that it's impossible to happen. Okay, it's impossible to happen. Even if you use a very bright light, okay, also cannot, because the chances of one electron to meet with two photon is really low. Okay, the chances are really low. That means if you want the electron to be able to meet with two photons, the light intensity, okay, they got calculate. If you want to increase the chances of the electron to meet with two photon and absorb energy from two photon, and the electron to have enough energy and escape to have photoelectric effect. And the brightness, the intensity of the light need to be, if I remember correctly, is like I think like 100 times the brightness of the sun. Okay, 100 times the brightness of the sun, then only is possible. Okay, so how is it that you can have a brightness of light that is 100 times the brightness of the sun? Okay, get the idea. So so that is why when we talk about photoelectric effect, we straight away assume that one electron only meet with one photon. It will not be able to meet with two photons. So in order to have photoelectric effect, the frequency, the energy of the photon must be enough, must be high enough for the electron to have photoelectric effect. Okay, so that means that is why we have threshold frequency. Okay, that is why we have threshold frequency. That means if the frequency is higher or equal to or higher than threshold frequency, then that means the photon will carry enough energy for the electron to escape the metal surface and become photoelectron, or we have a photoelectric effect lah. Okay, get the idea. Okay, so that is why we have the four characteristics of the photoelectric effect lah. So the first one, it says that the kinetic energy of the photoelectron does not depend on the intensity of the light. Okay, does not depend on intensity of the light. That means even if you use a very bright light, okay, the kinetic energy of the photoelectron will not be higher. Okay, because even if you have very bright light, at most is you have more photon. Okay, you have more photon shining down, so you can produce more photoelectron. But all of the photoelectron, because they only can meet with one photon, so all of the photoelectron will not be able to have more energy. Each photoelectron will only be able to have the energy from one photon, and that's it. Okay, so I repeat, one electron only can get energy from one photon. So if you want to increase the kinetic energy of the photoelectron, that means you want to make the photoelectron escape faster with higher velocity, then this frequency, the frequency of the light must be higher, must be much higher than the threshold frequency. The higher the frequency of the light, the greater the kinetic energy of the photoelectron. Okay, but of course the frequency must at least be higher than the threshold frequency lah. Okay, we want to look at differences between emission of electron from metal surface by thermionic emission with photoelectric effect. Okay, so the emission of electron from a metal surface by thermionic emission, it may take some time because you need to heat the metal. Okay, you need to heat the metal slowly, increase the temperature, and when the temperature increase, the kinetic energy of the electron will increase. Slowly increase until the electron have enough energy to escape. Okay, so then only the electron can escape lah. Okay, so this is thermionic emission. But for photoelectric effect, each packet of light, that means each photon, already carry enough energy for the electron to escape. So immediately when one photon go in, meet with electron absorb the energy, immediately the electron can jump out. So immediately you will have photoelectric effect when light shine on the metal surface. So that is the difference between the photoelectric effect and thermionic emission.